Today's video is brought to you by Bright Cellars, a fantastic way to find and try new wines from the comfort of your home. More on them in a bit. On cold winter nights in the Northern Hemisphere, when there isn't a cloud in the sky, one point of light amongst a sea of stars outshines all others. However, this is no star. A simple look through a cheap telescope will show you a fuzzy orange and brown circle and 4 other points of light. A planet, one large enough to fit 8 Earths across its equator. A planet that Earth and the rest of the solar system owe its current state to. 741 million kilometers from the Sun, Jupiter is the 5th planet in our solar system. Approaching its storm-ridden surface from the view of NASA's Juno probe, we get an impression of what it might be like to travel to the planet from a spacecraft, to gaze upon the most imposing planetary figure in our solar system from an uncomfortably close 3,299 kilometers from its raging outer layer of clouds. We have never been able to see this much detail on Jupiter before. Staring at its surface from this distance, Jupiter's impossible scale is on clear display. Many of its streams of clouds and storms are more than ample enough for the Earth to fit inside. Yet even before NASA's Juno probe, and before Galileo pointed his 20-power telescope up at the stars, we were captivated by the planet Jupiter. While Venus may indeed be Earth's evil twin and the brightest star near dawn, Jupiter's brilliance dominates the midnight sky like the Roman god of the same name, ruling from his throne on Mount Olympus. In Roman mythology, Jupiter, or Zeus to the Greeks, was the king of the gods and the most powerful being in his pantheon. But even in ancient times, Jupiter the planet was known to our species. The Babylonian epic Enuma Elish, translated from cuneiform as the Tablets of Creation, described Jupiter as the marker of the signs of the zodiac, stating that Marduk, the creator, named this point of light Nibiru. But this was only the planet's name when it was brightening the midnight sky of the Euphrates Valley. In 1610 AD, Galileo spent several nights in January observing 3 strange stars around Jupiter that seemed to move retrograde when compared with the rest of the stars. As his observations continued, he noticed a 4th star in the formation. Strangely, these 4 smaller points of light seemed to change their relative positions quite often. By the 8th night, Galileo came to the logical conclusion that these were not stars that he was seeing, but rather the planet Jupiter and several of its moons. In fact, these were the first moons ever discovered outside of the Earth-Moon system. Galileo Galilei took his findings as evidence that the Copernican theory was right and that the other planets did not revolve around the Earth. Given that he was the first to discover them, naturally he had the right to name these newly found moons and chose to name them after his patrons, the Medicis. While astronomers throughout the 17th century called them the Medician Stars, today we know them as the Galilean Moons: Europa, Callisto, Io, and Ganymede. In March of that year, Galileo published a book titled Sidereus Nuncius, the Starry Messenger. Funnily enough, Galileo referred to these moons in this work by Roman numerals in the order of their discovery, but famous astronomer Johannes Kepler suggested that Galileo named them after mythological figures related to Jupiter, even suggesting the names that we now use today. This idea would finally start to catch on 200 years later. In 1892, astronomer E.E. Barnard would discover the 5th of the current 79 Jovian satellites, and throughout the 20th century, we would learn that Jupiter's role in the solar system's tumultuous history was far more important than we could have hoped to imagine. Now, before we continue with today's video, maybe you're sitting there and thinking, well, I'd enjoy this video a whole lot more if I had a glass of wine in my hands. Well, good news for you. That's exactly what today's sponsor, Bright Cellars, can make happen. With Bright Cellars, you pop on over to their website, you take a super simple 7-question quiz. There's no snobbery, all easy questions to answer. And from that, they'll learn about your taste, palate, and the wines you're most likely to enjoy. And then they send them to you. And yes, they come direct to your door, so there's no wasting time in the liquor store guessing which one you're going to like based on how the label looks. Plus, you get to learn something about what you're drinking, as each wine comes with an education card, serving temperature, pairings, etc. all laid out. Look, I'm a big wine drinker, love wine, and with Bright Cellars, it's just an all-round better experience. Plus, each month your wines get better as you rate the ones you've already had, and Bright Cellars adapt what they're sending you to your tastes. For a limited time only, get 50% off your first 6-bottle box for a total of only $55, including shipping. Get started by going to brightcellars.com/geographics, take the palate quiz, see your personalized matches, and now back to today's video. With a radius of 69,911 kilometers and accounting for more than twice the combined materials of the other bodies orbiting the Sun, Jupiter is the largest planet in the solar system. But how exactly did it get so massive? By rights, Jupiter is larger than some stars, yet for some reason, Jupiter lacks the required mass and pressure needed for hydrogen fusion to occur. Jupiter and the Sun share an eerily similar composition, and their densities aren't all too different either. While Jupiter has a density of 1.33 grams per cubic centimeter, the Sun has 1.41, bringing to mind the outdated notion that Jupiter is a failed star. But stars and planets like Jupiter and Saturn form through very different mechanisms. Stars are born from nebulae called stellar nurseries. These nurseries are made up of gas that is gravitationally contracting in on itself. Eventually, the core of this cloud will collapse into what's known as a protostar, an object that lacks the hydrogen fusion of its main sequence elders. This new object will continue to accumulate material from an accretion disk that is formed from the remaining material in the stellar nursery. This stage in stellar evolution can stretch on for 100,000 to 10 million years, but once that protostar accumulates enough material to reach 0.08 solar masses, it will finally begin to burn hydrogen in its core. But even then, a new main sequence star like ours needs about 50 million years to mature. It is during this chaotic period that the accretion disk around the newly minted star begins to form the first planets and planetesimals from a swirling, dense molecular cloud. The first glowing hot giant planets emerge once there is enough condensation in that molecular cloud. Jupiter's formation began shortly after the Sun's graduation from protostar into main sequence star 4.5 billion years ago. For a long time, scientists thought that Jupiter and the other gas giants must have formed somewhere close to where they are now in the outer reaches of the solar system. That was until we started to look at other star systems in the Milky Way. Sitting at a distance of 35 light-years from Earth, 51 Pegasi b was the first planet to ever be discovered outside of our solar system. Scientists would be surprised to learn that 51 Pegasi b completes a single orbit in just 4 days at a distance that is much closer than Mercury orbits our Sun, meaning that temperatures can range from 1,000 to 1,800 degrees Celsius. Because of its close proximity to its star, this scorching vision of hell has a diameter 50% larger than Jupiter, despite the fact that it's 47% less dense. Of the 4,000-some odd exoplanets discovered as of November 31st, 2021, 400 of them are like 51 Pegasi b, known today as hot Jupiters. The discovery of hot Jupiters threw a massive wrench into our model for exactly how Jupiter and Saturn formed. If hot Jupiters were fairly typical in our galaxy, why was it that our gas giants evolved in such a different way? Up until the arrival of Juno in 2016, our data on Jupiter's interior structures was quite limited. Most of what we knew came from the Galileo spacecraft that was launched in 1989 and spent 8 years orbiting the gas giant. Juno unraveled many of the theories surrounding Jupiter's composition, but it also showed us a surprising picture of its core, informing new models on its origin. We have two predominant models for how Jupiter and other gas giants form: the core accretion model and the disk instability model. In the core accretion model, a heavy element core is the first part of the gas giant to form, followed shortly by the accumulation of large amounts of gas which will make up the planet's immense atmosphere. However, in the disk instability model, gas giants develop because of gravitational instability in the protoplanetary disk. This is then followed by the acquisition of heavy elements and shortly thereafter, the gas giant's core. Jupiter's history is a little more complicated than that. Currently, scientists think that it began its life forming at a distance 4 times further out than its current orbit. First, Jupiter's core would have formed from absorbing planetesimals, small, icy, kilometer-sized objects that are thought to be the building blocks of planets. The Sun's immense gravity would have drawn the still-forming Jupiter closer to it. The resulting 700,000-year journey would take the future king of the solar system on a spiral path around the Sun, gradually capturing Trojan asteroids that would later make up 2 swarms that occupy Jupiter's orbit today. Because of what researchers have learned from the gravitational data gathered by both Galileo and Juno, we now know that Jupiter contains far more heavy elements than we previously thought. In fact, because of this, the rocky core makes up 30% of Jupiter's entire mass, far more than we originally thought. This is huge because it means that Jupiter's core exerts far more gravity than its outer layers, and it gives a lot of credence to the grand Tack model, which we will be learning about shortly. Before Juno, we thought that Jupiter's composition would have been far more homogeneous than it really is. It turns out that the gas giant's contents mix about as well as oil and water. Due to this, researchers now believe that Jupiter would have spent nearly 2 million years gobbling up baby planets, delaying its runaway accumulation of gas. But that runaway gas accretion period would have happened eventually, leading to Jupiter becoming the largest object in our solar system. Its formation was instrumental to the future of other planets and their orbits, potentially even causing planetary collisions, like that of Theia and young Earth that is thought to have caused the formation of our moon, Luna. While some theories maintain that Jupiter and the other large planets would have started off closer to the Sun and then migrated to their current orbits, other evidence, such as a curious lack of rocky Earth-like planets that can range from around 2 to 10 times our planet's size, exoplanets known as super-Earths, suggest a very different story, one that paints the still-forming Jupiter in a light more akin to the Titan Saturn who devoured his own sun than the wise king of the gods. While there is no direct evidence that our solar system has ever had super-Earths, their overwhelming abundance in the Milky Way has led scientists to believe that there is a very good chance that they did exist at one point. If these researchers are correct, then Jupiter would have migrated far closer to the Sun, risking becoming one of those hot Jupiters that seem to be so common in the Milky Way. If there were super-Earths developing in the inner solar system during this extended journey, Jupiter would have wreaked absolute havoc on them, possibly causing them to either collide with each other or plunge into the Sun. Either way, their destruction would end up paving the way for second-generation planets like Mercury, Venus, Earth, and Mars to form from the path of destruction left in the wake of that journey. If there were no super-Earths forming in the inner solar system, then this journey and subsequent retreat would have created a gravitational environment where such a planet wouldn't be possible in the orbits of the 4 terrestrial planets. Known as the Grand Tack model, Jupiter's migration into the inner solar system would have started because of gravitational interactions with another planet, likely Saturn, and the protoplanetary disk. This interaction would, of course, spiral waves to propagate through that disk, and the two bodies would have migrated into the inner solar system. But something would have stopped Jupiter from flying too close to the Sun, like its hot Jupiter brethren and the mythical boy Icarus with his wax wings. The second largest planet in the solar system, Saturn, would have begun forming sometime after Jupiter's core began to take shape. Saturn's formation would have happened at a slightly slower rate. Jupiter's inward journey would have also dragged Saturn with it, and the two planets would have eventually developed an orbital resonance around 1.5 AU from the Sun, or in other words, where Mars orbits the Sun today. And that's where they would have begun to retreat from the inner solar system, eventually ending up in the orbits they occupy today. It is far more likely that the existence of the gas giants in their current orbits prevented the planets in the inner solar system from getting too large and preventing Earth and Mars from accumulating too much mass. But even after Jupiter and Saturn retreated to their current orbits, that wouldn't have been the end of their influence on the inner planets. Most models suggest that the formation of the gas giants would likely have left a lot of asteroids and planetesimals in the inner solar system, leading to what is known as the late heavy bombardment, which saw the young Earth and other inner planets experience an unprecedented number of impacts 3.8 billion years ago, the evidence of which is thought to be written on objects in the solar system like the moon's near side. The Grand Tack model might answer a lot of questions, but it doesn't have answers for all of our solar system's quirks. Questions like whether or not it's even possible for two giant planets to migrate into the inner solar system and then retreat. If Saturn is the reason for Jupiter's outward migration, how is it that it did not become as massive as Jupiter? And do gas giants even have solid cores? The answer to these questions, and many others, may very well be written in the complex composition of the king of the planets itself. Jupiter might be the largest planet in the solar system, but its magnetosphere is the largest object with an average radius of around 4,999,998 kilometers. That's 150 times wider than Jupiter and almost 15 times wider than the Sun. In fact, if Jupiter's magnetic field were an object visible in Earth's sky, it would be around the size of the full moon. The magnetic field is somewhat in the ballpark of 20,000 times stronger than Earth's and is thought to be produced by a complex dynamo system inside the planet. The magnetosphere traps charged particles, forming massive radiation belts similar to the Van Allen radiation belts that exist around the Earth. Scientists have been analyzing the radio waves coming from Jupiter for decades, and famously, the Voyager 1 spacecraft recorded these radio waves in the form of haunting audio tracks that people are still listening to today. Jupiter gives off high amounts of radiation, radiation that its inner moons absorb. This creates gaps in the field that are easily identified by scientists here on Earth. Voyager 1 also gave us definitive proof that Jupiter has rings, something that Pioneer 11 was only able to show hints at in the form of charged particle absorptions. Jupiter's poles are full of surprising features as well. The South Pole is dominated by 6 polar cyclones, and the Northern Pole features 9 of them. However, these features are somewhat overshadowed by the glowing brilliance of Jupiter's auroras, which are generated by charged particles that have been accelerated by the planet's magnetic field and sent crashing into the magnetic poles. Since the conclusion of Juno's first 5-year mission, descriptions surrounding Jupiter's surface have been revised quite a bit. These descriptions have been pulled from numerous scientific papers hoping to decode the data taken from the probe. Now, the portions of this outer layer that are white are known as zones, and the bands of red and brown colored clouds are called belts. These mysterious jet streams extend some 3,218 kilometers beneath the planet's top cloud layer. While scientists aren't sure how these jet streams are formed, Juno did show us that ammonia gas seems to follow those jet streams with almost perfect alignment. A day on Jupiter is equal to less than half on one of Earth, 10 hours. This incredibly fast rotation creates a powerful jet stream that separates out Jupiter's zones and belts. While Jupiter is composed primarily of hydrogen and helium, these zones and belts are thought to be plumes of sulfur and phosphorus containing gases that have risen up from the depths of Jupiter's warmer inner layers. Storms like the infamous Great Red Spot have raged for 300 years and can persist for decades and centuries thanks to the fact that the planet has no solid surface. The storms near Jupiter's equator can reach wind speeds as fast as 539 kilometers per hour. Juno also showed us that the clouds in the Great Red Spot are warmer on top and colder near the storm's bottom, with corresponding areas of lower and higher atmospheric densities. These storms are also much taller than we originally thought they would be. Thanks to gravitational readings from Juno, we now know that some of these storms extend 96 kilometers beneath Jupiter's cloud tops, while others, like the tumultuous Great Red Spot, can dig as deep as 482 kilometers into the planet's depths, which is far deeper than the sun's light can reach. In the year 2003, smaller storms were observed to merge together, forming what's now known as the Little Red Spot, which is around half the size of the Great Red Spot. Jupiter's cloud layers may stop at an average depth of around 64 some odd kilometers beneath the surface, but its atmosphere is far more complicated, reaching surprising depths. Most of the clouds in the uppermost cloud layer are more than likely composed of ammonia ice. The middle cloud layer is composed of ammonium hydrosulfide crystals, and finally, the innermost layer is most likely composed of ice and vapor. If you were to take a trip into Jupiter's depths, assuming you had a magical spacesuit that would allow you to survive, the cloud layers would gradually become denser and wetter, until eventually you would reach a point inside Jupiter where the pressure gets way more intense, where hydrogen cannot remain in its gaseous state. One moment you would be falling through dense clouds, and the next you'd be swimming in Jupiter's immense ocean. Beneath Jupiter's complex atmospheric layers, possibly at a depth of around 12,000 kilometers, where pressures reach between 400 and 500 gigapascals and temperatures can get as hot as 20,000 degrees Celsius, the hydrogen that is so common in Jupiter's atmosphere is transformed into an ocean of liquid hydrogen. With depth of 40,233 kilometers, this is the largest ocean in the solar system. At this depth, it is believed that the pressure is so intense that electrons are stripped from hydrogen atoms. This means the liquid hydrogen ocean is as conductive as metal is here on Earth. And we call this state metallic hydrogen. This unique form of hydrogen is an example of what's known as a supercritical state. In most cases, these are metastable states of matter that exist solely between a range of temperatures and pressures. Unlike on Earth, where the dynamo process is thought to mostly take place in the outer core, Jupiter's is likely generated closer to the surface, or more accurately, near the boundary between Jupiter's upper layers and its metallic hydrogen ocean. It is at this point that scientists believe that metallic hydrogen ocean is at its most conductive. However, Juno was able to peer much further into the planet's interior than the metallic hydrogen ocean, revealing secrets about Jupiter's core that might one day settle one of the oldest debates in astronomy. Does Jupiter have a solid, amorphous core? Originally, NASA planned for Juno to meet its demise by crashing into Jupiter's cloudy surface in January 2021, but its mission was extended to September of 2025. This will provide it with more chances to study Jupiter's complex atmosphere and structure. One of the most tantalizing questions in astronomy is whether or not gas giants like Jupiter and Saturn have solid rocky cores. Juno's analysis of Jupiter's core was somewhat shocking to the scientific community in that it did not reveal a solid core in the traditional sense, but rather a fuzzy thing that seems to be spread throughout half of the gas giant's diameter. Given Jupiter's climactic past, it's easy to see why scientists think that this feature could be due to a large planetary impact that might have happened during the Grand Tack. Such an impact may explain why the planet's magnetic field appears to be so different in the south versus the north. Remember when we mentioned that Jupiter's heavy elements make up about 30% of the planet's mass? It's for this reason that scientists now believe they have conclusive proof that Jupiter's core is composed of heavier rocky elements, meaning that it is probably solid. But speaking of impacts, Jupiter has a long history of impacts and is often seen as Earth's protector in a sense. But this is more akin to myth than to actual fact. In reality, Jupiter's relationship with life here on Earth is quite complicated, and perhaps there is no better way to explain that complicated relationship than with the story of Comet Lexell. In 1770, Charles Messier was hunting for comets, cataloguing anything that wasn't a comet in the now famous Messier catalogue, when he observed a comet grow brighter and brighter in its path through the night sky. At the point of the comet's closest approach to Earth, Comet Lexell looked quite strange to Messier, featuring a massive head several times larger than the full moon and a bright tail. Messier never saw Comet Lexell again, but to today's astronomers, it's clear what actually happened. After reverse engineering Comet Lexell's approximate path, they discovered that its original orbit may have been altered by Jupiter to one that would take it uncomfortably close to our planet, at about 2.2 million kilometers from the surface. In fact, Comet Lexell is the only comet in recent history to get this close to our planet. To explain the comet's disappearance, it is thought that later on Jupiter would have re-encountered the comet and its interaction would have ejected it from the inner solar system. So in as little as 12 years, interactions with Jupiter are likely to have both sent a dangerous object perilously close to the Earth and also removed said object from the inner solar system, playing both villain and hero. Jupiter is a complex and fascinating planet, and while its immense gravitational presence might have sculpted our solar system in what it is today, it is more akin to a Jekyll and Hyde figure than the great defender of the Earth that it is sometimes made out to be. As this video comes to its close, it's important to note that we've only just begun to answer some of the great many questions that Jupiter has raised throughout humanity's storied history. There is no doubt that we have even more jaw-dropping discoveries to look forward to regarding the King of the Planets and its chaotic origin. Here's looking forward to what else NASA's Juno probe can show us in the near future.